Hi, my name is Kennedy Rand, and this is my Lab 2 video report on charged tapes as lines of charge. The purpose of this lab was to further develop our knowledge of how charged objects interact with our surroundings by creating a more sophisticated and accurate model for charge. We built upon our initial calculations in charge 1 by treating the tape as a line of charge instead of as a point charge. We then used this model to calculate a more accurate value for the charge of the tape through our code. The result was found that the positively charged tapes, when in equilibrium and modeled as line charges, have a charge of about 2.42 times 10 to the negative 8 coulombs, which is much greater than the value found in Lab 1. So to achieve the goals of this experiment, I used several fundamental principles of physics. First, I used the law of attraction to determine the sign of the tape's charge. I also was able to use Newton's second law, which states that an object in equilibrium has a net force of 0, to set up an equation for the electric field. Finally, I was able to use Coulomb's law to derive an equation to calculate the charge of the tape. To carry these calculations out, we had to assume that each U-tape had the same amount of charge, the charge was uniformly distributed across the tape, and forces due to air resistance are negligible. The methodology for this experiment was the same as Lab 1. First, I had to create multiple charge tapes, and this procedure is represented in the top right. Next, I had to determine the sign of the charge of the tape. I did this by holding the tape up to a negatively charged pen. Because the tape was attracted to the pen, I determined that the tape was positively charged. Finally, I created two charged tapes and set them up so that one would hover in equilibrium above the other, as depicted in the diagram on the bottom right. From here, I recorded the distance between the tapes to use in future calculations. After noting the mass and length of each tape and the distance between the tapes, I was able to move forward in my calculations. First, we noted that because the floating tape is not in motion, we can conclude that the sum of the forces acting on the top tape is 0. The only forces acting on this tape are the force of gravity acting downward and the electrical force from the bottom tape acting upward, as represented in the free body diagram. So, knowing that the gravitational force is equal to mass times gravity, I calculate this value to be about 0.002 newtons, which is equal and opposite in magnitude to the electric force. Before moving on to the rest of the results for Lab 2, it's important to note where Lab 1 and Lab 2 differ. From this point in Lab 1, I was able to derive Coulomb's law to calculate the charge of the tape when treated as a point charge, and got a value of 9.7 times 10 to the negative 9th coulombs, as you can see above. However, since we are now modeling the tapes as lines of charge, we would expect the value for charge in this lab to be different. Here we can see the output from the Lab 1 code on the left, which modeled the tapes as point charges. As you can see, the blue tape or floating tape is in equilibrium. When I set up the original code for Lab 2 and put in my known values, and I used the value for the tape's charge from Lab 1, it gave me this output on the right. The gravitational force is represented by the yellow arrow, and the electric force is represented by the super small white arrow in the middle. Here we can clearly see that the value for charge from the previous lab is much too small for this new model, as the gravitational force and electric force are not in equilibrium. Thus, the first step I took to set up this model for Lab 2 was to increase the value of Q so that the forces would be in equilibrium again. And after trial and error of adjusting this value, I was able to get a Q value that balanced the forces of about 2.42 times 10 to the negative 8th coulombs, as labeled by the red arrow, and the original value for Q from Lab 1 is listed below this new value. The new value is about 2.5 times greater than the original value. From this point, I was able to walk through the code to look at each piece of the model. The first piece of the model utilized my previous function for calculating electric field and is labeled by the orange arrow. The next piece involved a function to create a model for the tapes as line charges and is labeled by the purple arrow. The lines of my code that utilize this function and created the tapes are labeled by the red arrow. Next, this function here iterates through each small piece of the bottom tape for each small piece of the top tape. So essentially, we're breaking the top tape into small pieces and treating the bottom tape kind of like a charged rod acting on each of these small pieces. We're gathering the electric force acting on each of the small pieces of top tape by the rod, as shown by the green arrow, and then summing each of these to get the total electric force acting on the entire top tape, labeled by the blue arrow. Lastly, I was able to create arrows in the visual output to represent both the electric force and the gravitational force, as seen by the green and blue arrows respectively. Finally, all of this code combines to produce the output of the code on the right. The green arrows represent the electric force acting on each small piece of the top tape. The white arrow represents the total net electric force acting up, and the yellow arrow represents gravitational force acting downwards, which are equal in magnitude and opposite in direction, as you can see in the output text. Finally, in conclusion, we can examine the difference between our results from Lab 1 and Lab 2. When modeling the tapes as line charges instead of as point charges, as we did in Lab 1, we see that our value for charge increases by around 150%, or is about 2.5 times greater than the original value. In Lab 1, when modeling our tapes as point charges, we had to assume that all of the charge across the entire tape was concentrated at one point. However, we know that in reality, the charge of the tape is distributed across the entire tape. In Lab 2, we thus were able to model the tapes as line charges to more closely depict the way that it is in the real world, and thus obtain a much more accurate value for the charge of the tape. Thanks for watching.